Welcome back, ladies and gentlemen. Today we're going to be talking about diatomic molecules to continue our conversation about covalent bonding, because diatomic molecules are actually two atoms of the same element that are bonded together chemically. I think of them as elements. Some people think of them as molecules. It really depends on how you work with them. This is the elemental form of these molecules. They will never come as single atoms. Every single one of these particular elements will only come as diatomic molecules. You never find them in nature by themselves. So while they're two atoms chemically bonded, making them a molecule, they are the elemental form of this particular substance. There is no other way that these are found. So remember the elements that form diatomic molecules. It's really simple. We're going to use a mnemonic device, and the mnemonic device is Brinkelhof. Brinklhof. And if you haven't figured out, those represent the elements. They are the symbols of the elements. So Br stands for bromine, I stands for iodine, N stands for nitrogen, Cl stands for chlorine, H stands for hydrogen, O stands for oxygen, and F stands for fluorine. So we can see that we have 7 elements that form diatomic molecules, and there are only 7 on the periodic table. And these are those 7. Let's look at them again. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now, I can tell you very clearly that bromine, iodine, chlorine, hydrogen, and fluorine are going to behave similarly. Well, why do they behave similarly? They are similar because they all want only one electron. They want / need only one electron to be an octet. Of course, hydrogen doesn't need an octet, but you get the idea. All of those, bromine, iodine, chlorine, hydrogen, and fluorine, 5 of them. There are 5 of them that only need a single electron. So they will only form single bonds. They are the only ones that only form single bonds. So when we look at oxygen and nitrogen, we'll see some weirdness going on with that. So let's look at an example of one of those 5. And all of these 5 will be represented by the same kind of idea. Obviously, the electron configurations will be a little different, but the same ideology is in play for those 5. Bromine, iodine, chlorine, hydrogen, and fluorine. And you notice bromine, iodine, chlorine, and fluorine are in the same group. They're all halogens, so they're going to behave the same way anyway. All right, so here we go. We see fluorine here, and we see the electron configuration for fluorine, and we notice that both of them are missing an electron. Both of them are missing an electron. So what's going to happen is each has 7 electrons, so we get one fluorine next to the other. This fluorine comes with its 7 valence electrons. This fluorine comes with its 7 valence electrons. And then right here in the center, we have the bonding pair, one from each. This is where the bond is formed to make the F2. We have FF right here. There's the bond that's forming that. It's only a single bond because it's a single pair of electrons being shared. So all of the ones, bromine, iodine, chlorine, fluorine, and hydrogen, all behave this way because they're only going to make a single bond between them. So that is the diatomic fluorine molecule. It also would be representative if you replaced Cl or Br or I for F. You'll get the same thing. The only difference between H is that instead of having all of these peripheral valence electrons, they only have one each, so they will only be sharing these and have no electrons around them. All right, so let's move to oxygen. Now we see oxygen's a little different. Oxygen has 6 valence electrons each, so each of these needs 2 valence electrons. Well, the only way that that can happen is if each oxygen shares 2 electrons with the other oxygen. So here we go. Here there are 2 oxygens. Here's the first one. Notice they're rearranging. And this is really key here because we can rearrange valence electrons. We want to give electrons as much room as they possibly can need. And so we are rearranging here with these electrons. Notice the 2 from this oxygen that is going to be shared with this oxygen. The other oxygen is going to do the same thing. You have these two being shared by this oxygen with this oxygen. So now we have 1, 2 bonds, or a double bond. This is where we're seeing a double bond. A double bond is 2 pairs of electrons being shared. And when oxygen forms a diatomic molecule, that's exactly what it does, because each oxygen needs 2 electrons to complete its octet. And now if we count 1, 2, 3, 4, 5, 6, 7, 8, that one has 8. 1, 2, 3, 4, 5, 6, 7, 8, and that one has 8. So we can see that both of them are going to have 8 valence electrons at some point in time. Nitrogen gets even trickier because we notice that nitrogen is missing 3 electrons. Each has 5 valence electrons. Well, to make this even with each of them, they will both have to share 3 electrons. So this is what's going to happen. Nitrogen is going to throw a pair of electrons over here, and then all the 3 lone electrons are going to go over here to be shared. This nitrogen is going to do the same. So you can see you have 1, 2, 3 bonds, and this is a triple bond with 3 pairs of electrons being shared. So that's the diatomic molecules and how that works. So hopefully you'll have an understanding of that a little bit better, and we'll get into a little more complicated Lewis dot structures probably tomorrow. Thank you.